Tonight we are going to wander quietly to the very edge of everything we can know. And then just a little further than that. 2 trillion galaxies. That is what our observable universe holds within it, a sphere stretching 93 billion light-years across in its full diameter. When you first encounter that number, it sounds like an answer. It sounds like the complete inventory of all that is. And in one sense, it is genuinely breathtaking. But here is the quiet thought that tends to get left out of that sentence. What we can see is almost certainly a vanishingly small fraction of what actually exists. Not because our telescopes are pointed in the wrong direction. Not because we lack the resolution to peer far enough into the dark, but because the physics that gave rise to a universe capable of supporting life also guaranteed, structurally and permanently, that most of existence would remain out of reach. Tonight, we are going to follow that reasoning all the way to its conclusion through the mathematics, through the horizons, through the anomalies flickering at the edges of our best maps, and out the other side, as far as the equations will carry us. Get settled, take a slow breath. We have a long and genuinely wonderful journey ahead of us. There is a number in cosmology so precisely calibrated that when physicists first worked out what it ought to be versus what it turned out to actually be, some of them found themselves wondering, in a deeply serious way, whether the universe had somehow been arranged. That number goes by the name omega. And what omega describes is not the shape of any particular galaxy, not the curve of space around a black hole, not even the geometry of our local cosmic neighborhood. Omega describes the overall shape of space itself, the curvature of the cosmos taken as a whole, at the very largest scales we are capable of measuring. When the Planck satellite, the most sensitive instrument humanity has ever aimed at the sky, completed its survey and returned its final measurements, the value it recorded for omega was 1.0, give or take 0.5%. In the language of cosmology, that means the universe is flat, not roughly flat. Not approximately flat in the way a calm ocean looks flat on a clear day. Flat to within 0.5%, measured across a volume of space so large that no human mind can form a sensory impression of it. Let's sit with that for a moment, because it deserves more than a quick nod. A single light year is the distance light covers in a full year of uninterrupted travel, about 5.88 trillion miles. Multiply that by 93 billion, and you have a number that would exhaust any pen before you finished writing it down. Across that entire incomprehensible expanse, we have measured the geometry of space and found it balanced hovering at exactly 1. That should produce in you a feeling not of fear, but of the particular unease you get when a magic trick is so cleanly executed that you cannot quite figure out where the trick is hidden. Because here is what makes flatness in cosmology so quietly alarming. It is not the natural resting condition of space. It is not a state that the universe gravitates toward over time the way a spinning top gradually settles to a stop. In the mathematical framework that governs how the universe grows and changes, flatness is what physicists call an unstable fixed point. A balance so precarious that the slightest nudge in any direction sends everything careening away from it. Think of trying to balance a pencil on its tip. It can be done with extraordinary steadiness for a brief moment, but any deviation, any tremor sends it falling. And the longer the pencil has been in motion, the further from vertical it has wandered. Space follows the same logic. If Omega had begun its existence even slightly above 1 by even the tiniest imaginable margin, then gravity, the self-attraction of all the matter in the universe, would have been just sufficient to win out over the outward rush of the Big Bang. Space would have expanded to some maximum extent and then reversed, collapsing inward in a catastrophic implosion cosmologists call the Big Crunch. We are talking about a universe that might have survived for a few 100,000 years before folding back into nothing. No time for stars to form, no time for planets, no time for anything at all. And if Omega had begun just slightly below 1, the opposite story would have played out. Expansion would have won so decisively that matter never found the chance to pool and clump under gravity. The universe would have become an ever-thinning, ever-cooling haze of gas drifting outward into a perfect and featureless dark. No galaxies, no stars, no carbon. No one sitting where you are right now letting these ideas drift through a sleepy mind. The gap between those two outcomes is extraordinarily narrow. And what makes the numbers truly staggering is this. For Omega to equal 1 to within 0.5% today, at this particular moment in the 13.8 billion year history of the cosmos, the value it started with at the very first instant of the universe, at what physicists call the Planck time, which sits at 10 to the negative 43 seconds after the beginning, would have needed to equal 1 to within 1 part in 10 to the 62nd. Write that out slowly. 1 followed by 62 zeros in the denominator. That is the degree of precision with which the initial conditions of this universe appear to have been set. If that opening value had differed from 1 by even a single unit in the 62nd decimal place, the universe would have either collapsed or dissolved before a single star had time to ignite. This is what cosmologists call the flatness problem, and calling it merely a problem understates the situation somewhat. It is not the kind of thing you resolve by shrugging and saying the universe just happened to start that way, because accepting that answer requires accepting that out of all the possible ways a universe might begin, the effectively infinite range of values that Omega could have taken, the one that actually occurred, was so precisely calibrated that winning a lottery 17 consecutive times looks, by comparison, like a fairly ordinary afternoon. And here is where the story opens into something far larger, because physicists did not simply stand at the edge of this impossibility and stare. They found a mechanism. Or rather, they proposed one. A mechanism so extreme, so brief, and so thorough in its consequences that it left almost no direct trace in the observable universe, and yet its fingerprints are written into literally everything we can see. That mechanism is called cosmic inflation. And once you understand what inflation actually does, not just to the flatness problem, but to the very boundaries of what is observable, the universe begins to look quite different from the one most people carry in their heads when they glance up at the night sky. Inflation is not the ordinary expansion of space that has been proceeding gently for the last 13.8 billion years. It is something of a different order entirely. It is a period in the very earliest universe lasting somewhere between 10 to the negative 36 seconds and 10 to the negative 32 seconds after the, beginning a window so brief that comparing it to anything in human experience is essentially meaningless, during which space underwent exponential expansion at a scale that has no analogy in anything else we know. The universe grew by a factor of at least 10 to the 26th. Some models suggest far greater. To feel what that number means, consider a single atom something already far too small for human senses to detect directly. Inflate it by that factor, and it would emerge from the process larger than the entire observable universe we see today. That is the scale of what happened. What inflation does to the flatness problem is both elegant and almost brutal in its thoroughness. Imagine standing on the surface of a sphere. If the sphere is basketball-sized, the curvature is obvious. You could feel it, see the horizon curving away from you. But as the sphere gets larger, the curve becomes gentler. Stand on something the size of Earth and the ground feels perfectly level, even though you are living on a ball. Now take that progressive flattening and apply it at a factor of 10 to the 26th. Any original curvature in the early universe, any departure from perfect flatness that Omega might have begun with, would be stretched so completely that from our position inside the post-inflation universe, it would be entirely undetectable. Inflation does not require Omega to have started at exactly 1. It takes whatever value Omega had and drives it toward 1 with such overwhelming force that whatever it began at becomes cosmologically irrelevant. Inflation solves the flatness problem. But solutions in physics rarely come without a cost. And what inflation costs is something most people have never fully reckoned with. Because if inflation stretched space by at least that factor of 10 to the 26th, that stretching did not stop neatly at the boundary of what would later become our observable universe. It stretched everything. It took regions of space that were, before inflation began, close enough to our region that light could have passed between them regions that could, in principle, have been observed or interacted with, and pushed them so far away that no signal traveling at the speed of light will ever reach us from them. Not in 1 trillion years. Not in 100 trillion. Not ever. The sphere we can observe 93 billion light-years across, home to roughly 2 trillion galaxies, is not the universe. It is a small and local patch of a far vaster structure. And that larger structure is hidden from us not by the limits of our technology, not by a temporary gap in our knowledge, but by the same physics that made our existence possible in the first place. The mechanism that solved the flatness problem is identical to the mechanism that guaranteed we would never see most of reality. There is a calculation that tries to put a lower boundary on how large the actual universe must be. In 2011, researchers Vardanyan, Trotter and Silk published a careful Bayesian analysis drawing on the flatness constraints from the Planck data. What their work found was that under the simplest inflationary models consistent with what we observe, the real universe must have a radius at least 251 times that of our observable sphere. 251 times. That translates into a volume roughly 15 million times larger than everything we have ever seen or mapped. And that is the minimum, the conservative number you get from the most restrained models. Under many perfectly reasonable inflationary scenarios, the actual extent is incomparably larger, possibly infinite. This is not fringe thinking. This is what you arrive at when you take the Planck satellite's measurements seriously and follow the mathematics wherever it leads. The mainstream data-grounded reading of modern cosmology is that we are enclosed within a causal bubble, a sphere defined not by the outer wall of the universe, but by how far light has had time to travel since the beginning. Beyond that bubble lies a structure so enormous that calling it more universe barely begins to capture what we mean. So here is the question threading through everything we are about to explore. What kind of physics creates a universe in which most of itself is permanently concealed from anyone who could ever look? Not hidden by accident, not hidden until better instruments arrive, hidden by structure woven into the very equations that determine how space grows. That is what we are going to find out. And I will say now, gently, that the answer does not get simpler the closer you look. It gets stranger. Let's be specific about where you are right now. As these words drift through your mind, you are sitting at the exact geometric center of a sphere with a radius of approximately 46.5 billion light-years. Not near the center. At the precise center, and so is every other observer in the universe, wherever they happen to be. That is not a statement about human significance. It is a direct consequence of how observation works in an expanding universe, and understanding it is the first step toward grasping just how thoroughly inflation has hidden most of what exists. The observable universe is defined by a single physical constraint: how far light has managed to travel since the universe became transparent, about 380,000 years after the beginning. Before that moment, the cosmos was a dense, hot plasma of charged particles, an opaque fog through which photons could not freely move. When the universe cooled enough for electrons and protons to settle into neutral hydrogen, photons were released and began their long journeys outward in every direction. The oldest light we can detect has been traveling ever since, for 13.8 billion years. But here is where common intuition tends to trip people up, and it is worth pausing on carefully. Those ancient photons did not cross 46.5 billion light-years by moving faster than light. Space itself has been expanding throughout their journey. The universe kept growing while the photons were in motion, stretching the distance between their point of origin and us. By the time they arrive, the object that emitted them now sits roughly 46.5 billion light-years away, accounting for all that expansion. This is called the comoving distance, and it is the difference between how long the light has been traveling and how far the source has actually receded. The edge of our observable sphere is not 13.8 billion light-years out. It is 46.5 billion, because the universe never stopped growing while the light was crossing it. Every observer anywhere in the universe sits at the center of their own sphere of this same size. An alien civilization in a galaxy near what we perceive as our observable edge would have its own sphere centered on itself, overlapping with ours in some directions, extending well beyond us in others. Their sky holds galaxies we will never see. Their observable universe looks, from the inside, just as complete and total as ours does from within. This is the illusion of totality, the way a finite local window can feel from inside it like the whole thing. Inside our sphere, the numbers are extraordinary. Recent estimates suggest there are approximately 2 trillion galaxies within the observable universe. To put that in terms that feel at least a little more tangible if you try to count them at the rate of 1 per second, never stopping, never pausing even to sleep, it would take you over 63,000 years to finish. The Milky Way alone holds somewhere between 100 billion and 400 billion stars. And the Milky Way is, in the cosmic ledger, an entirely ordinary galaxy. Not unusually large, not unusually small, one of 2 trillion. The observable universe contains, by most careful estimates, something on the order of 10 to the 24th stars, a 1 followed by 24 zeros, more than the grains of sand on every beach and every desert on Earth, combined and multiplied several times over. And yet, as we have established, this is a small portion of the total. The boundary of our observable sphere has a name and a real physical presence. It is called the cosmic microwave background, the CMB, and it is one of the most quietly extraordinary things in the sky. Not simply because of what it is, but because of what it reveals about the limits of our reach. The CMB is not a wall, and it is not empty space. It is the surface of last scattering the shell of the universe at the moment it first became transparent, preserved for us in the form of radiation. In every direction, if you could tune your perception to the right frequency, you would see this glow a nearly perfect field of thermal radiation at a temperature of 2.725 Kelvin, or about negative 270.4 degrees Celsius. Barely above absolute zero, extraordinarily uniform. Almost featureless, but not quite. The CMB is not where the universe ends. It is a boundary in time the furthest back we can see using light of any kind. Beyond it, in every direction, space continues. Before that moment of transparency, it existed as an opaque plasma, and beyond it, in the sense of the region's inflation pushed past our causal reach, it continues as something we can only infer. The CMB is not the edge of the universe. It is where our line of sight reaches its limit, for now using electromagnetic radiation. There are signals that originate from even earlier. The cosmic neutrino background, for instance, decoupled from matter roughly 1 second after the beginning, a full 380,000 years before the CMB photons were released. Neutrinos interact with matter so weakly that they streamed free almost immediately after the Big Bang. In principle, detecting that background would let us see the universe as it existed in its very first second. In practice, we have not yet built an instrument sensitive enough to capture it directly, though its presence is inferred from CMB measurements and from our models of how the first light elements formed. And even earlier than the neutrino background, there are gravitational waves generated during inflation itself, ripples in the fabric of space-time produced when inflation stretched quantum fluctuations up to cosmic proportions. These waves, if detected, would be the oldest signal physically possible, encoding information from the inflationary epoch directly. We have not confirmed them yet, though the polarization pattern of the CMB, specifically a component called B-mode polarization, may eventually reveal them to instruments of sufficient sensitivity. The night sky, then, is not a window onto the full universe. It is a local record. A partial map, a two-dimensional projection of a sphere that is itself just one small region of a structure incomparably larger. The familiar feeling of looking upward and sensing the entire cosmos spread out above you is a product of our limitations, not a picture of reality. You are seeing the neighborhood, not the city. Not the continent, and certainly not the vast expanse that inflation stretched permanently beyond your reach. The observable universe is not a description of what exists, it is a description of what the physics of space-time permits us to access. One of the most persistent misconceptions in cosmology is the idea that there is a single edge, one clean boundary out there beyond which things simply stop, or beyond which our instruments cannot peer. The reality is both more complicated and considerably stranger. There are actually several distinct horizons in cosmology, each one defined by a different physical constraint, and they do not agree with one another. Understanding why they differ is central to understanding what inflation actually accomplished, and what it means for the permanent concealment of most of reality. The particle horizon is what most people have in mind when they speak of the observable universe. It sits at approximately 46.5 billion light-years and marks the furthest distance from which light could have reached us across the entire history of the cosmos, accounting for expansion. Anything within this boundary has been in causal contact with us at some point. Some photon, some signal could have traveled from there to here. This horizon reflects the age of the universe and the history of its expansion, and inflation shaped its character by smoothing and flattening the region we inhabit and establishing the starting conditions from which everything inside it evolved. Then there is the cosmic event horizon, which sits at a much closer distance of about 16.6 billion light-years. This is not the limit of what we can see, it is the limit of what we can ever meaningfully interact with. The boundary beyond which, given how cosmic expansion driven by dark energy is expected to proceed, any message we send today will never reach its destination, and any signal sent from beyond that point will never arrive here. It is defined not by the past, but by the future, by the ongoing acceleration of expansion that is steadily widening the gulf between us and distant galaxies. The Hubble sphere is something else again, sitting at roughly 14.4 billion light-years. This marks the distance at which galaxies are currently moving away from us at exactly the speed of light. Inside the Hubble sphere, galaxies recede more slowly than light. Beyond it, they recede faster. This does not break the rules of relativity. Space itself is expanding, not objects pushing through space. But it does create an interesting situation. Photons currently sitting outside the Hubble sphere and aimed toward us are, at this moment, actually losing ground. The space between them and us is growing faster than they can cross it. Over time, as the universe expands, the Hubble sphere itself grows, and those photons gradually find themselves in a region of slower recession and can begin making progress again. And then there is the future visibility limit at roughly 62 billion light-years in moving distance, the farthest objects that will ever become visible to us as the universe continues to age, including photons currently in transit that have not yet arrived. What ties all of these together and brings us back to the central thread is this. Right now, we can see galaxies, some of them in beautiful detail, that we will never visit, never communicate with, and that will eventually vanish from our sky entirely. Dark energy is accelerating the expansion of space. Over sufficient time, distant galaxies will redshift beyond any instrument's ability to detect them, their light stretched to wavelengths too long to capture. The observable universe, in the deepest causal sense, is actually contracting, not in that the sphere of past visibility shrinks, but in that the set of objects we could ever hope to reach or hear from grows smaller with every passing year. Inflation set the initial scale of what is hidden. Dark energy is quietly extending that concealment with every passing second. Here is a question that sounds slightly absurd when you first encounter it. How do you measure the overall shape of the universe? Not the local curvature of space around a massive object, not the shape of a galaxy, the global geometry of the cosmos itself. How do you draw a triangle large enough to test whether its angles add up to 180 degrees or to something different? The answer involves the cosmic microwave background, and it is one of the most elegant observational achievements in the entire history of science. In a flat universe, the rules of ordinary geometry hold at every scale. Triangles sum to 180 degrees, lines that begin parallel stay parallel. But in a positively curved universe one, where omega exceeds 1, Like the surface of a sphere, parallel lines eventually converge, and the angles of a large enough triangle add up to more than 180 degrees. In a negatively curved universe, like a saddle shape, parallel lines diverge and triangle angles sum to less. The CMB gives us a ruler to work with. Before the surface of last scattering, the hot plasma of the early universe was not perfectly still. Pressure waves moved through it, sound waves driven by the competition between radiation pushing outward and gravity pulling inward. These waves had a characteristic scale set by how far sound could travel in the early universe at that time. When the universe became transparent and the CMB was released, those waves froze in place, leaving a pattern of slightly warmer and cooler regions imprinted across the sky. The spacing between those frozen peaks and troughs is known very precisely from the physics of plasma. Now, if you know the physical size of that ruler, and you can measure the angle it appears to span across the sky from our vantage point, you can calculate the geometry of the space through which its light has been traveling. In a flat universe, a ruler of known size at a known distance subtends a specific angle. In a positively curved universe, it appears larger. In a negatively curved one, smaller, this is the cosmic triangle test. The first major modern result came from the Boomerang Experimenter balloon observatory that circumnavigated Antarctica in 1998 and 2000, measuring the CMB at degree scales with then unprecedented precision. Boomerang found that the first acoustic peak in the CMB's temperature pattern sat at a multipole moment of approximately 220, exactly where flat geometry models predicted it would fall. Then came MAP, the Wilkinson Microwave Anisotropy Probe, which refined these measurements considerably between 2001 and 2010. And then came Planck, the European Space Agency satellite that operated from 2009 to 2013 and returned the most precise CMB data ever collected. Planck confirmed flatness at the level we have already discussed, omega equal to 1 within 0.5%. The acoustic peaks fell precisely where flat geometry requires. Independent confirmation came from a different direction entirely, baryon acoustic oscillations. Those same frozen sound waves detected not in the CMB but in the large-scale distribution of galaxies. The clustering pattern of matter across the universe carries the imprint of those early pressure waves, and that imprint, measured across surveys of hundreds of millions of galaxies, agrees with the CMB flatness measurements to remarkable precision. But there is a wrinkle, the kind of wrinkle that has been keeping a subset of cosmologists quietly wakeful. The Planck data showed a slight anomaly in the way the CMB's temperature pattern is blurred and shifted by the gravitational pull of intervening matter, a process called gravitational lensing. The lensing signal was slightly stronger than flat geometry models predicted, hinting at roughly 2 to 3 sigma significance, not enough to declare a discovery, but too consistent and too large to dismiss at a universe that might be very slightly positively curved. If real, this would push omega just above 1 and suggest a finite spherical universe rather than an infinite flat one. The tension has not been resolved. Combined data sets that include galaxy surveys and baryon acoustic oscillations still favor flatness. But the lensing anomaly persists as a quiet reminder that our measurements, as precise as they are, still carry uncertainties. And those uncertainties matter enormously, because this is precisely where the connection to inflation becomes critical again. The extreme flatness that Planck measured is not something that could exist without inflation or something functionally equivalent to it. Classical Big Bang cosmology, without an inflationary phase, simply cannot produce a universe this flat. And inflation, as we have established, did not stop at the edge of our observable sphere. The same measurement that confirmed flatness is the measurement that implies everything we cannot see. Let's go a little deeper into the mathematics of why flatness is so unsettling. Because I think it is easy to hear the phrase 1 part in 10 to the 62 and let it wash over you the way very large numbers often do in cosmological conversations as just another impressive sounding quantity in a field full of impressive sounding quantities. It is not that. It belongs to a different category from other fine-tuning results in physics, and sitting with it properly matters for understanding why inflation is treated so seriously by so many careful scientists. In standard Big Bang cosmology without inflation, omega follows a specific evolution as the universe ages. The deviation of omega from 1, call it omega minus 1, grows over time during the matter-dominated era and grows even faster during the earlier radiation-dominated period. What this means technically is that omega equal to 1 is an unstable equilibrium. Like the pencil balanced on its tip, any universe with omega even slightly off from 1 will drift further and further from 1 as time passes. The deviation does not remain small. It compounds. Now run that equation backward. Today, omega equals 1 to within 0.5%. Travel back 10 billion years to the era of the first stars. Omega had to have been even closer to 1 at that point. Travel back to the epoch of Big Bang nucleosynthesis, about 3 minutes after the beginning. When protons and neutrons first began fusing into helium and deuterium at that moment, omega had to match 1 to within roughly 1 part in 10 to the 15th. Go back to 1 second after the beginning, 1 part in 10 to the 18th. Go back to the Planck time, 10 to the negative 43 seconds, 1 part in 10 to the 62nd. That is the precision requirement imposed on us by the equations of general relativity applied to an expanding universe, not as an approximation, as a mathematical necessity. Is there any known physical principle that would naturally drive omega to exactly 1 in standard Big Bang cosmology? There is not. No symmetry, no conservation law. No known mechanism points toward 1 as a special or preferred value. It is purely an initial condition. And asking why that initial condition should have been so extraordinarily precise is, in the classical framework, like asking why a bullet fired from an enormous distance hit a target the size of a proton. There is no mechanism. You have to assume it was aimed. The flatness problem connects deeply to a second puzzle, the horizon problem, and together they make the case for inflation almost impossible to set aside. The horizon problem is this. The temperature of the CMB is uniform across the entire sky to 1 part in 100,000. Everywhere you look, including in directions directly opposite each other, separated by regions that in standard Big Bang cosmology had no way of ever communicating the temperature, is identical. How? 2 regions of the universe that have never been in contact cannot generally be expected to share the same temperature. If you placed a hot cup of tea and a glass of cold water at opposite ends of a very long table and they never came anywhere near each other, they would not find their way to the same temperature on their own. They would stay as you left them. And yet the CMB tells us the universe achieved thermal equilibrium across distances larger than light could have crossed in the time available. In classical Big Bang cosmology, this simply has no explanation. Inflation resolves both problems with the same mechanism. Before inflation, the region that would eventually expand into our entire observable universe was smaller than a proton, in some models considerably smaller, and all of it was in causal contact. Thermal equilibrium could be established, curvature could be smoothed. Inflation then stretched this tiny, smooth, equilibrated patch into something vastly larger than our observable sphere. The CMB is uniform because before inflation, everything we can see was a single connected region. And the universe is flat because inflation erased every trace of curvature from our observable patch and buried whatever remained so far beyond our horizon that it will never return. There is a third problem that inflation addresses, sometimes called the monopole problem. At the extreme temperatures of the early universe, quantum field theory predicts that phase transitions occurred as things cooled, transitions something like water freezing into ice, but happening in the fundamental fields of physics rather than in molecules. These transitions should have produced exotic particles called magnetic monopolies, hypothetical objects with a single magnetic pole, either north or south, but not both. Grand unified theories, which attempt to bring three of the four fundamental forces under one framework, predict that monopolies should have formed in enormous numbers in the early universe. We have never detected a single one. Either they do not exist, which would rule out a large class of unified theories, or something diluted them to concentrations too low to find. Inflation does this perfectly. If monopolies formed before inflation began, the subsequent exponential expansion would have distributed them across so vast a volume that the expected number within our observable universe today would be essentially zero, consistent, quietly, with what we observe. Three separate, seemingly unrelated puzzles in classical cosmology. One mechanism inflation that resolves all three simultaneously. This is not the usual shape of progress in physics, where a new idea fixes one problem and creates two others. This is a single physical process eliminating three independent paradoxes with one stroke. That kind of convergence earns serious attention. It is the sort of thing that makes physicists trust a theory even before direct confirmation has arrived. But every solution, as we keep finding, carries a cost. Inflation resolving the flatness problem means it stretched our observable patch out of a far larger hole. Inflation resolving the horizon problem means the regions now beyond our horizon were, before inflation, part of the same small equilibrated patch as ours, and inflation carried them past the boundary. Everything that was once in causal contact with us, everything that shared our early conditions, most of it now lives permanently beyond reach. We inhabit a fragment of what was once a unified expanse. And the fragmentation was not temporary. The story of inflation begins with a problem that has nothing to do with flatness or horizons. It begins with a young particle physicist named Alan Guth working at Stanford in the winter of 1979 and 1980, trying to figure out why grand unified theories predicted magnetic monopolies that experimentalists had simply never found. He was not approaching the problem as a philosopher of cosmology. He was approaching it as a physicist bothered by a specific mismatch between theory and observation. The answer he arrived at, which he described in his research notes from that period as a spectacular realization, was that a brief phase of exponential expansion in the very early universe would not only scatter any monopolies to vanishingly low concentrations, but would simultaneously resolve the flatness problem and the horizon problem. He published in 1981, and the effect on the field was immediate and lasting. Guth's original formulation has been considerably refined since, but the essential idea persists. In the very early universe, the dominant form of energy was not matter or radiation, but the energy stored in a quantum field, what physicists now generically call the inflaton field. This field was trapped in what is called a false vacuum, a configuration that was locally stable but not at the lowest possible energy. Think of a ball sitting in a shallow hollow on a hillside. It rests there for a while, but if it crests the rim, it rolls down to the valley below. The hollow is the false vacuum. The valley floor is the true vacuum. While the inflaton field sat in its false vacuum, it behaved like a cosmological constant, a form of energy spread uniformly through space that does not thin out as space expands. The energy scale was roughly 120 orders of magnitude higher than the dark energy we observe today, and it drove exponential expansion at a rate that makes current cosmic expansion look essentially frozen by comparison. Exponential expansion is worth dwelling on for a moment because it behaves unlike anything in ordinary experience. Space does not grow at a steady rate. It doubles in some extremely short interval, then doubles again in the same interval, then again. If the doubling time were 10 to the negative 37 seconds, then after 10 to the negative 36 seconds space has doubled 10 times a growth factor of around 1,000. After 10 to the negative 35 seconds, it has doubled 100 times a factor of 10 to the 30th. The total growth factor emerging from the models is at minimum around 10 to the 26th, and in many models considerably more, depending on how long the inflationary episode lasted. To understand what this means for the relationship between inflation and the observable universe, it helps to think backward. The observable universe today spans a radius of 46.5 billion light-years. Before inflation, the region that would expand into everything we can see today was smaller than a proton, perhaps much smaller, depending on the specific model. After inflation expanded it by that minimum factor, it became vastly larger than our observable sphere. The portion of the inflated volume that falls within our observational reach is a tiny fraction of the total that inflation created. Andrei Linde, a Russian-American physicist who became one of the central architects of inflationary theory, introduced what became known as chaotic inflation in the early 1980s. Linde demonstrated that inflation did not require the exotic phase transitions of grand unified theories to get started. It could arise far more naturally from a scalar field with a simple energy landscape, one where the field begins at a high value, rolls slowly toward its minimum, and drives exponential expansion throughout the slow roll. Chaotic inflation is robust, flexible, and connects naturally to ideas about what might have surrounded or preceded our particular inflationary event. Inflation ends when the inflaton field reaches the bottom of its energy landscape, the true vacuum, and its energy is transferred into the particles of ordinary matter. This process is called reheating. It is the moment that marks the start of the hot Big Bang that most people picture when they think of the origin of the universe. The fireball of matter and radiation that eventually evolved into galaxies, stars, and planets was not the beginning. It was what came after inflation concluded. The Big Bang, in this picture, is not the creation of the universe. It is the moment inflation stored energy converted into ordinary warmth and matter. The universe existed in some form before that as a nearly featureless, rapidly expanding expanse of vacuum energy. Reheating has observable consequences. The infleton field did not flow uniformly into matter and radiation. Quantum mechanics, which operates everywhere and always, introduced tiny fluctuations into the field during its slow roll. These are not imperfections in the engineering. They are fundamental. The uncertainty principle forbids any quantum field from being perfectly smooth. During inflation, these fluctuations were stretched from subatomic scales to cosmic scales by the expansion. After reheating, they became slight variations in matter density regions, fractionally denser and fractionally less dense, spread across the universe at scales set by the rate and duration of inflation. These density variations are what gravity later amplified into the large-scale structure we see today, the filaments and sheets and clusters of galaxies that trace the cosmic web. The statistical properties of these variations, specifically their amplitude and how that amplitude varies with scale, are directly measurable in the CMB. Inflation predicts what is called a nearly scale-invariant power spectrum, meaning fluctuations have roughly equal amplitude across all scales, with a slight lean toward less power at smaller scales. The Planck satellite measured the spectral index characterizing this spectrum at 0.9649 plus or minus 0.0042. The prediction from simple inflationary models is a value slightly less than 1. The measurement is 0.9649. The agreement is quietly extraordinary. Inflation also predicts primordial gravitational waves ripples in spacetime, generated by the same quantum process that produced density fluctuations, leaving a specific imprint in the CMB's polarization pattern called B-mode polarization. This has not been definitively detected at the time of this script, though the search continues with instruments including BICEP and the Simons Observatory. Detecting it would measure the energy scale of inflation, directly a result of Nobel-caliber significance and likely within reach of the next generation of experiments. But here is the line that connects all of this to the central story. Every fluctuation that inflation stretched to cosmic scales, every perturbation that became a galaxy, a cluster. A void was once a quantum wiggle smaller than an atom. Inflation is the process by which the quantum becomes cosmic. And while it was doing that for the region that became our observable universe, it was doing the same for the far vaster regions it stretched beyond our horizon. Those regions contain their own fluctuations, their own density variations, their own structures formed from identical physics, evolving under identical laws that we will never observe. Inflation created both the universe we can see and the boundary we cannot cross. In 2011, 3 cosmologists, Miran Vardanyan, Roberto Trotta, and Joseph Silk, published a paper addressing a deceptively plain question. Given everything we currently know, given the full suite of measurements from Planck and WMAP and every other relevant instrument, what is the smallest the actual universe could be. They approached this using a statistical framework called Bayesian model comparison, a rigorous way of asking which hypothesis the data most supports, while appropriately penalizing models that require many adjustable parameters. They considered a range of geometries and global topologies, and asked what minimum size was required for each to remain consistent with the observational data, specifically the constraint that the universe appears flat within the measured precision. Their result is the number introduced early in this journey. The universe must have a radius at least 251 times that of our observable sphere. Multiply 251 by 46.5 billion light-years, and you arrive at a minimum radius of approximately 11.7 trillion light-years. Volume scales as the cube of the radius, so the minimum volume works out to 251 cubed, roughly 15.8 million times the volume of everything we can see. 15.5 million observable universes minimum packed into the actual universe. Consider what that means for the total count of galaxies. 2 trillion in our observable sphere multiplied by 15. 8 million gives a minimum total somewhere around 32 sextillion. That is 32 followed by 21 zeros. Every single one of them invisible to us, not because our telescopes lack the power, but because inflation carried them beyond the boundary of causal contact. These are not unusual or exotic galaxies. They formed from the same physics, seeded by the same quantum fluctuations, stretched by the same inflationary epoch. They are, statistically speaking, much like the ones we do see, ordinary and forever out of reach. And 251 times the observable radius is, to be clear, the lower bound. The most conservative figure, derived from the simplest inflationary models assuming curvature, sits at the very edge of what observations allow. Many well-motivated models, especially those where inflation lasted longer or began from initial conditions further from flatness, predict extensions vastly beyond this. And then there is a whole class of models in which the actual universe is not merely very large, but genuinely mathematically infinite. An infinite universe has a consequence that takes a moment to absorb. In a universe that extends without limit in every direction, filled with matter distributed roughly uniformly on large scales, every possible arrangement of matter and energy will occur not just once, but endlessly, including an exact replica of the Milky Way, including an identical solar system, including a planet where someone is at this moment listening to these words and thinking about the size of the universe. The estimated distance to the nearest exact copy of our observable universe in an infinite flat cosmos has been placed at roughly 10 to the power of 10 to the 118 meters, a number that cannot be meaningfully visualized and barely be written. Yet in an infinite universe, that is simply a finite distance. Not infinite, just very, very, very large. This is not mysticism. It is the direct logical consequence of combining an infinite universe with the observed uniformity of the CMB and the known rules of quantum mechanics, which limit the number of distinct quantum states possible within any finite volume. If the universe is infinite, repetition is not a poetic idea. It is an inevitable mathematical outcome. We do not know whether the universe is infinite. What we know is that it is at minimum vastly larger than anything we can see. The inflationary solution to the flatness problem, the same solution that made our existence possible, is the mechanism that guaranteed most of the universe's content is permanently beyond our reach. The map is radically incomplete. And what lies off the map is not emptiness. It is more of the same, more galaxies, more complexity, more history, more of everything just permanently invisible from here. So far we have been working with a natural assumption that space beyond our observable horizon simply continues in the way it does inside it, an ever-extending expanse, either infinite or at least incomparably vast, more of the same stretching outward in every direction. And that assumption is not unreasonable. It is the default picture, what you arrive at if you take the Planck flatness measurement and simply let it run. But there is another possibility, one that does not require the universe to be infinite and does not require it to have a boundary. What if the universe is genuinely finite, in volume countably finite, and yet has no edge? What if space folds back on itself in such a way that if you travelled far enough in a perfectly straight line, you would eventually arrive back where you started? I know that sounds like the premise of a story rather than a scientific proposal. It is not. It is a mathematically well-defined possibility that serious cosmologists have explored for decades, and it connects to a distinction in mathematics that is worth understanding clearly. Because once you have it, it reshapes how you think about the shape of everything. The distinction is between geometry and topology. These words are often treated as interchangeable in everyday conversation, but in mathematics they refer to genuinely separate things, and conflating them causes most of the confusion around this subject. Geometry describes local curvature, the rules that govern measurement in the neighborhood around any given point. It tells you whether parallel lines converge, diverge, or stay parallel, whether the angles of a triangle sum to 180 degrees or something else. Topology describes global shape, how the space is connected at its largest scales. What happens not between two nearby points, but if you keep traveling in one direction for a very, very long time. And here is the insight that makes this interesting. The same local geometry can correspond to many entirely different global topologies. Local flatness does not determine global shape. They are separate questions with separate mathematics. A concrete example helps. Take a flat, two-dimensional surface. The simplest topology for such a surface is an infinite plane flat in every direction, extending forever. If you lived on it and drew triangles, everyone would sum to 180 degrees. Perfectly Euclidean. But now take a square piece of paper, connect its left edge to its right edge, and you get a cylinder. Then connect the top circle of the cylinder to the bottom, bending it around until they meet. You get a torus, the surface of a donut. That surface is still locally flat. Draw a small triangle anywhere on it, and the angles still sum to 180 degrees. You could not determine from local measurements alone that you were on a torus rather than a plane. But if you started walking in one direction and kept going, eventually you would return to your starting point. The surface is finite. It has no edge, no wall, no point where space stops. It simply wraps. Extend that idea to 3 dimensions. Harder to picture because we lack a convenient extra-spatial dimension to fold through, but the mathematics is perfectly coherent. A 3-torus, sometimes called a hypertorus, is the 3-dimensional version of the same construction. Imagine a cube. Identify the left face with the right face. Identify the top with the bottom, and the front with the back. Walk through the right wall and you reappear through the left. Float up through the ceiling and drop back through the floor. Space is locally flat. All local measurements satisfy Euclidean geometry. consistent with what Planck measured, but it is globally connected in this looping way. The universe would be finite in volume, with no center, no edge, and a character that will feel familiar to anyone who has played the original Pac-Man, where leaving one edge of the screen brings you in on the opposite side, except in all three spatial dimensions simultaneously. This is not a marginal idea. The possibility of a toroidal universe was explored in depth by two of the most influential Soviet cosmologists of the 20th century, Yakov Seldovich and Alexei Starobinsky, in the 1970s and 80s. Starobinsky, notably, is the same physicist who developed one of the most successful models of cosmic inflation. These were not figures at the fringes of the field. The reason topology matters observationally is that a toroidal universe would leave a specific signature in the CMB. If space loops back on itself at a scale comparable to or smaller than our observable sphere, then looking outward in certain directions, we would effectively be seeing the same region of space from two different angles, once the short way around the loop, once the long way. The CMB temperature pattern in those directions would match exactly. Because it is the same physical region, what you would see, if you knew how to look, is pairs of circles on opposite parts of the sky, where the temperature fingerprints are identical. Cosmologists call these matched circles, and they would be the definitive observational signature of a finite, topologically non-trivial universe. The Planck satellite searched for them. Its topology analysis, published in 2015, examined the CMB sky systematically across a wide range of angular scales. It did not find them. And this is where the result becomes interesting in a subtle way, because the absence of a detection is not a refutation. It is a constraint. What the non-detection tells us is that any topological identification scale the distance at which space loops back must exceed about 1.2 times the diameter of our observable sphere. In other words, if the universe is a 3 torus, the loops are too large to show up within the region we can see. The matched circles, if they exist, sit just beyond our horizon. We cannot rule out a toroidal universe. We can only rule out a small one. And given what inflation almost certainly did to the scale of the universe, a toroidal topology with loops that exceed our observational reach is entirely consistent with everything we know. Inflation would have stretched the topological scale along with everything else, pushing any wraparound structure well beyond the causal boundary. The two ideas, inflation and finite topology, are not in tension. They coexist comfortably. There are more exotic topological possibilities as well. The Picard horn is one of three-dimensional space shaped, roughly speaking, like an infinitely long trumpet. It has finite volume, but an infinite funnel extending in one direction. Researchers have examined whether its specific mathematical properties might explain some of the anomalies visible in the CMB at the largest angular scales, specifically the fact that the biggest temperature fluctuation modes have slightly less power than simpler models predict. The Picard horn has not found compelling observational confirmation, but neither has it been definitively ruled out. Those large angle CMB anomalies are worth a moment's attention on their own, because they sit in the data persistently, appearing in multiple independent analyses. The quadrupole and octupole, the largest scale temperature variations in the CMB, have less power than a purely random isotropic infinite universe would statistically produce. Whether this reflects finite topology, a statistical fluke, residual contamination from foreground sources, or something else entirely, remains genuinely unresolved. It is the kind of small, stubborn feature that keeps drawing careful scientists back, not because it demands an extraordinary explanation, but because it quietly refuses to disappear with improved data. And here is what ties all of this back to the thread running through everything. Even if the universe is finite and topologically connected, even if space truly does wrap back on itself at some vast scale, inflation still determines what portion of that architecture we can observe. Topology describes the global structure of space. Inflation describes the causal horizon, the boundary within which any signal can have reached us. Those are logically independent of each other. A toroidal universe could be perfectly finite, with a well-defined total volume. And yet inflation could have pushed our observational horizon well inside a single topological cell. In that case, everything accessible to us would look indistinguishable from a genuinely infinite flat universe. The wraparound structure would be real. It would be a genuine feature of space's global organization, and we would have no means of detecting it from here, not because our instruments are insufficient, but because the causal boundary inflation constructed sits closer to us than the scale at which the topology would become apparent. The hidden majority of reality is hidden not by its topology. It is hidden by the causal boundary that inflation drew into the structure of space-time. Whether what lies beyond that boundary is infinite or finite, wrapped back on itself, or something more unusual still, the boundary itself is the thing. Inflation drew the line. And everything we are exploring, every model, every measurement, every anomaly, every geometric possibility, is our attempt to reason about what sits on the other side of a wall we built ourselves, without meaning to. In the first fraction of a second of existence, there is a further consequence of inflation that carries us to the edge of what can currently be tested, and possibly past it. But before you feel yourself drifting away from the subject at the mention of the word multiverse, I want to say something clearly. What we are about to consider does not begin with speculation. It begins with the same mathematics that makes inflation compelling in the first place. It follows, step by step, from the same quantum physics that produced the density fluctuations we have measured in the CMB. The multiverse is not something cosmologists reached for because it sounded exciting. It is something the equations keep pointing toward, whether they are invited to or not. It is called eternal inflation, and it may be the most radical implication of everything we have explored so far. To understand it, we need to return to how inflation works in the models that best fit the data. The leading class of inflationary models, those whose predictions align most closely with what Planck measured, are called slow-roll inflation models. The name reflects the behavior of the inflaton field, the quantum field, whose energy drives the exponential expansion of the early universe. In these models, the inflaton field starts at a high value on its energy landscape. Imagine a ball resting high on a very gently sloping hill and rolls slowly downward toward its minimum. While it rolls slowly, its energy is high and relatively stable. That high, stable energy is what drives the exponential expansion. Inflation continues as long as the field rolls slowly. When the field reaches the bottom of the hill, inflation ends, its energy transfers into matter and radiation, and the hot Big Bang begins. That is the classical picture. Quantum mechanics does not care about the classical picture. Quantum mechanics imposes fluctuations on top of the smooth classical rolling. The inflattened field, like every quantum field, cannot be perfectly uniform and perfectly still. The uncertainty principle forbids it. So as the field rolls classically downhill, quantum fluctuations ripple through it constantly, randomly nudging the field value slightly up or slightly down around its classical trajectory. In most places and at most times, the classical rolling wins. The field moves downward and inflation ends on schedule. Those fluctuations are small perturbations riding atop a dominant trend, and they are exactly the density variations that inflation stretch to cosmic scales, the ones we have measured in the CMB. We know they are there. But here is what André Linde recognized in the mid-1980s, and it is one of those moments in theoretical physics where a simple observation carries consequences so large they take years to fully absorb. In some regions of inflating space, the quantum fluctuations will, by random chance, be large enough to push the inflattened field back up the hill against the direction of classical rolling. Not often. Not even regularly. But quantum mechanics is probabilistic, and in a universe undergoing exponential expansion, rare events happen continuously because space is always creating new volume in which they can occur. Inflation is exponential. Space is doubling and doubling again on timescales so brief that the numbers resist any human analogy. In any given region, the chance that a quantum kick delays inflation locally might be very small. But the total volume of inflating space is growing exponentially as well. New inflating regions are being generated faster than old ones terminate. And in any region where inflation is delayed by a quantum kick, the same process applies again. Those regions keep expanding, keep producing new volume, keep generating new fluctuations, some of which again delay inflation locally. The consequence which Linde worked out carefully, and which has been elaborated on by many physicists since, is that inflation, once it begins, does not fully stop. It ends locally in pockets, regions where the classical rolling prevailed. The field reached the bottom of its potential, and reheating occurred. Our observable universe is one of those pockets. The hot Big Bang that we tend to think of as the beginning of everything is, in this picture, not a beginning. It is a local ending of inflation, the moment when our particular region of inflating space transitioned into a warm, matter-filled cosmos. But surrounding our pocket, and surrounding every other pocket, inflation continues. It is always ending somewhere and always beginning somewhere else. The process is self-sustaining and, by the mathematics, eternal into the future. This is called eternal inflation. The structure it produces is sometimes called the inflationary multiverse, or the landscape of pocket universes. Each pocket universe begins with its own version of reheating its own local Big Bang, with initial conditions set by the specific state of the inflaton field in that region at the moment inflation ended. And this is where the picture becomes genuinely remarkable. Because those initial conditions are not necessarily the same in every pocket. String theory, the leading candidate for a theory of quantum gravity, though still unconfirmed by experiment, predicts an enormous landscape of possible vacuum states. A vacuum state, in this context, is not empty space in the everyday sense. It is the lowest energy configuration of a particular arrangement of the fundamental fields of physics. Different vacuum states correspond to different values of the physical constants, different strengths of the electromagnetic force, different masses for elementary particles, different values of the cosmological constant. The number of possible vacuum states in the string theory landscape is estimated at around 10 to the power of 500. That number so far exceeds the total number of atoms in the observable universe roughly 10 to the 80 that comparing them fails to convey the difference. In the eternal inflation picture, when a pocket universe forms and reheating occurs, the inflaton field's energy deposits into whichever vacuum state that region of space settles into. Different pockets forming at different times and locations in the eternally inflating background may settle into different vacua, which means they would have different physics, different values of the fine structure constant, different electron masses, different strengths of the nuclear forces, potentially different numbers of large spatial dimensions, different cosmological constants, different quantities of dark energy built into their fabric. They would be universes in the fullest sense governed by their own constants, evolving according to their own rules, producing their own structures, or failing to produce any if their constants landed in regions of the landscape incompatible with complexity. This is what physicists mean by the string theory landscape in a cosmological context. Not a catalogue of mathematical abstractions, but in the eternal inflation framework, a catalogue of actual places, pocket universes, each one a cosmos unto itself, each permanently inaccessible from every other, separated not by distance, but by the inflating background that will always fill the space between them. Whether any of this is testable is the sharpest question in the field, and the honest answer is that direct confirmation lies probably beyond any experiment we can currently conceive. But indirect evidence is not impossible, and one candidate deserves attention. Bubble universes in the eternal inflation framework are predicted to occasionally collide as they expand. A collision between two bubble universes would deposit energy asymmetrically into the CMB of each, leaving a specific circular imprint, a disk of anomalous temperature with a distinctive profile at its edge, in a region that would otherwise be statistically uniform. The CMB cold spot has been raised as a candidate. It is a region roughly 5 degrees across in the southern sky that is anomalously colder than virtually any standard inflationary model predicts for a feature of that angular size. It was identified by Vielva and colleagues in 2004 and confirmed by subsequent analyses. Current scientific consensus leans toward a large supervoid at a redshift of around 0.2 as the more likely explanation, a region of space with below-average matter density through which CMB photons lost energy via what is called the integrated Sachs-Wolf effect. That explanation is well supported by galaxy surveys, but it does not fully account for the temperature deficit. The cold spot remains slightly colder than the supervoid alone predicts. The bubble collision hypothesis, while not favored, has not been conclusively excluded. That is where we stand. The multiverse is a genuine prediction one that follows from eternal inflation, which follows from the quantum physics that inflation requires to generate the fluctuations we actually observe. It is not speculation in a costume. It is the logical end of a chain of reasoning that begins with the Planck satellite's measurement of the CMB spectral index and extends to places cosmologists are still working out how to think about. Some physicists remain genuinely skeptical, not because the mathematics is flawed, but because a prediction that cannot be tested raises real questions about what physics is meant to accomplish. That debate is unresolved and worth taking seriously rather than brushing past. What the multiverse represents, whatever its ultimate standing, is the outermost layer of inflation's consequences. not simply more space beyond our horizon, not merely more galaxies cut off by the causal boundary, but the possibility that the hiddenness of reality extends past the merely spatial, past the merely vast, into something categorically different, other spacetimes with other physics, other values of the constants that allow atoms to hold together, stars to shine, and chemistry to exist. The boundary inflation built inside our universe may be the smallest of the walls. Beyond it, if eternal inflation is correct, lies a structure so immense and so varied that our observable universe, 2 trillion galaxies, 46 billion light-years of depth, 13.8 billion years of history, would not register as a rounding error in its total account. And we are here, inside our bubble, reading its walls for clues. The cosmic microwave background is the most studied object in all of cosmology. Not the most studied thing in our solar system or our galaxy, the most studied object in the entire history of human scientific inquiry. It has been mapped by 3 generations of increasingly sensitive experiments, analyzed by hundreds of independent research teams, and subjected to every statistical tool modern cosmology has devised. Papers about the CMB appear every week. Careers are built on its subtler features. And mostly remarkably, almost breathtakingly, mostly it agrees. The standard cosmological model with its flat geometry, its inflation-generated perturbations, its cold, dark matter, and its cosmological constant produces predictions for the CMB that match observations with a precision that should make you pause and appreciate what physics has accomplished. The acoustic peaks sit exactly where they should. The spectral index matches the slow-roll inflation prediction within a fraction of a percent. For a model built on events that occurred 8 billion years ago, under conditions no laboratory can replicate, the agreement is extraordinary. But not entirely. There are anomalies, small enough that no single one would compel you to rethink the standard model, but persistent, showing up independently in WMAP data and then again in Planck data, surviving multiple analysis methods, sitting stubbornly in the numbers after every known source of contamination has been carefully removed. They are the kind of anomalies that serious scientists do not wave away, because the history of physics contains too many cases where a small, stubborn discrepancy in clean data turned out to be the first whisper of something genuinely new. The CMB cold spot is the most discussed. Identified in 2004 by Patricio Vielva and colleagues using a mathematical filter called the spherical Mexican hat wavelet, it is a region in the southern CMB sky, roughly centered on the constellation Eridanus, that is anomalously cold. The region spans approximately 5 degrees across, which in CMB terms is 10 times the width of the full moon on the sky. The temperature deficit there exceeds what standard inflationary models predict for a feature of that size. The probability of such a cold region occurring purely by chance sits somewhere between 1 and 2% unlikely, but not impossible on its own. The leading candidate explanation is a supervoid at a redshift of around 0.2, through which CMB photons lost energy via the integrated Sachs-Wolf effect. Galaxy surveys have found evidence for an underdense region in roughly the right direction. But the supervoid does not fully account for the observed temperature deficit. The cold spot is still slightly colder than the void alone predicts, and that gap has not vanished with more data. A small but careful community of physicists continues to ask whether something else is contributing, including, at the edges of the conversation, the possibility of a collision with an adjacent bubble universe in the eternal inflation framework. The axis of evil is a different kind of anomaly, and in some ways a more quietly unsettling one. It concerns not a single unusual patch, but the largest scale structure of the entire CMB map. When the temperature pattern is decomposed mathematically into its broadest components, the quadrupole and the octupole those components should, in a universe whose initial conditions were generated by an isotropic process like inflation, point in statistically random directions. They do not. Both are aligned with each other to a degree that is statistically improbable, and both are aligned with the ecliptic plane, the plane of Earth's orbit around the Sun. The probability of this occurring by chance in a genuinely isotropic universe is less than 1%. Foreground contamination is the obvious first response, and cosmologists have worked hard to remove it through multiple independent methods. The anomaly diminishes but does not disappear. Whether the residual is a systematic artifact no one has quite modeled correctly, or a genuine feature of the primordial CMB, has no settled answer. The third anomaly arrives from a completely different direction, the large-scale distribution of distant quasars. A study using the Catwise catalogue measured the dipole of the quasar distribution, the asymmetry in their numbers across the sky. Our motion through the universe produces a known dipole signal in the CMB, and it should produce a predictable corresponding dipole in distant sources. The two should agree. They do not. The quasar dipole is approximately 4 standard deviations larger than the CMB dipole predicts. 4 sigma is not a small discrepancy. It suggests either a systematic artifact in the data or a genuine large-scale asymmetry in the distribution of matter extending to the farthest distances we can map, which would challenge one of the foundational assumptions of the standard model. None of these anomalies has crossed the 5 sigma threshold required for a confirmed discovery. It is entirely possible they will each resolve into mundane explanations as surveys improve. But it is also possible they are not flukes, that they are genuine impressions left by something at or just beyond the boundary of our observable universe, a topology pressing on our largest scales. An inflationary geometry not perfectly symmetric, just beyond our horizon, a bubble collision waiting to be confirmed. The possibility is being investigated with real mathematical care. The universe has left its impressions inside our bubble. Most of them trace out the standard model with clarity. But a few are slightly smudged in ways that the standard model alone does not fully explain. And in science, it is almost always the smudges that lead somewhere worth going. Everything we have covered has treated the size of the observable universe as essentially fixed 46.5 billion light-years, 2 trillion galaxies, a sphere whose boundary was established in the first fraction of a second. That is not the full picture. The observable universe is changing, and the direction of that change, the progressive concealment of most of what exists, is being made steadily worse by one of the most consequential discoveries in modern science. It is called dark energy. And the deeply uncomfortable reality is that we do not fully know what it is. Dark energy is the name we give to whatever is causing the expansion of the universe to accelerate. Not just expand, accelerate. The universe is growing larger, faster and faster, and has been doing so for roughly the last 5 billion years. We know this because of Type 1a supernovae, stellar explosions consistent enough in their intrinsic brightness to serve as reliable distance markers across the universe. In 1998, two independent teams, the Supernova Cosmology project, led by Saul Perlmutter, and the High Z supernova team, led by Brian Schmidt and Adam Rees, were attempting to measure how fast cosmic expansion was slowing down. Gravity should have been doing exactly that. Both teams found the opposite. The distant supernovae were fainter than expected, meaning farther away. Meaning the universe was expanding more slowly in the past than it is today. Something was pressing the accelerator. Both teams spent considerable time checking for errors before accepting the result. They found none. The discovery earned the Nobel Prize in Physics in 2011, and it remains one of the most genuinely surprising results modern science has produced. The simplest model for dark energy is Einstein's cosmological constant, the energy of empty space itself. A baseline hum persisting even when all matter and radiation have been removed from a region. It fits the data reasonably well. But it comes with what physicists call, without much exaggeration, the worst prediction in the history of science. Quantum field theory predicts a vacuum energy density approximately 120 orders of magnitude larger than what we actually observe. That is not a small discrepancy. It suggests something fundamental is missing from our understanding. Either quantum field theory is wrong about vacuum energy in some deep way, or some mechanism cancels the predicted value almost perfectly, leaving just the tiny residual we see. No one knows what that mechanism would be. This is why results from the dark energy spectroscopic instrument DESI have attracted such concentrated attention. DESI is mapping the three-dimensional positions of tens of millions of galaxies across a wide span of cosmic history, using baryon acoustic oscillations to trace how the expansion rate has evolved. The first year of DESI data, released in 2024, produced a statistically interesting suggestion that dark energy's equation of state parameter may not be constant, but evolving with time. A changing dark energy parameter would rule out the cosmological constant model and imply something more dynamic, perhaps a slowly rolling scalar field, not unlike the inflaton field that drove inflation in the early universe. The parallel between the two is striking, and has motivated unified models in which a single field is responsible for both the exponential expansion at the beginning and the gentle acceleration we observe today. Whether those models are correct is unknown. The cosmological community is watching DESI's next data releases carefully. What all of this means for the central story is stark. The cosmic event horizon, the boundary beyond which we can never again receive information, is currently shrinking. Galaxies sitting just inside that boundary today will drift beyond it across billions of years and go dark, their light redshifted into wavelengths no instrument can detect. The number of galaxies accessible to us in any causal sense is decreasing, not increasing. Project this forward and the picture becomes quietly desolate. In roughly 100 billion years, about 7 times the current age of the universe, the only galaxies remaining visible will be those gravitationally bound to our own, the local group, a few dozen galaxies held together against expansion by their mutual gravity. The Andromeda Galaxy. The Magellanic Clouds. A handful of smaller companions. Everything beyond that will have faded to invisibility. Future astronomers, if any exist, will survey a sky containing a tiny fraction of the galaxies we can currently count, with no way of knowing from their observations alone that the universe once held 2 trillion. The evidence will have disappeared. The universe will have concealed its own history. We happen to exist at a cosmologically fortunate moment early enough that the sky still contains 2 trillion galaxies, that the evidence of inflation remains legible in the CMB, that the large-scale structure of the cosmos is still visible in galaxy surveys. Observers who come later will inherit a quieter sky and a universe that has done a far more thorough job of hiding itself. We are seeing more of it right now than anyone ever will again. Let's step back from all of it. From the flatness problem and the precision of 1 part in 10 to the 62. From inflation stretching space by a factor of at least 10 to the 26th in less than a billionth of a second. From the CMB's acoustic peaks sitting exactly where flat geometry predicted. From the 251 minimum radius and the 15 million observable universes of content it implies. From the topological possibilities, the Hyperterus, the Picard horn, the Pac-Man universe wrapping back on itself at scales we cannot reach. From eternal inflation and its foam of pocket universes. From the anomalies flickering at the edge of our best maps. From dark energy tightening the window with every passing eon. Step back and look at what it adds up to. These threads do not form a collection of separate puzzles. They form a single coherent story about something more specific and more strange than the mere size of the universe. It is a story about why what we can observe is not an accident of technology. Not a temporary limitation of our instruments, not a problem the next generation of telescopes will solve. It is a structural feature of how space-time itself is organized. The hiddenness of most of reality is not incidental to this universe, it is constitutive of it. The same physical process that made this universe livable, that smoothed its geometry, seeded its structure, created the conditions for stars and planets and carbon and us, is the same process that hid most of the universe from us permanently. Not temporarily. Not pending better instruments. The boundary was written into the physics at the same moment the physics wrote us. Our existence and our ignorance are not separate facts. They are 2 consequences of one event, distinguished from each other only by the direction you choose to look at the equations. The observable universe is a causal bubble. It is the sphere defined by the maximum distance from which any signal traveling at the speed of light through an expanding universe could have reached us across all of cosmic history. Everything inside that sphere has had the possibility of causal contact with us. Everything outside it has not, and in most cases not ever, because inflation stretched those regions so far beyond our reach that the expansion of space will always outpace any signal they could send. The wall is not a physical barrier. There is no membrane, no change in the texture of space at 46, 5 billion light years. Galaxies exist beyond it. Stars, perhaps planets, physics operating exactly as it does here. The boundary is not a property of that space. It is a property of the relationship between that space and us, the fact that no information from there can reach here. The wall is made of causality, not matter. This is where the holographic principle enters, elevating the horizon from an observational limit to something with genuine physical substance. The core idea, developed by Gerard Hooft and Leonard Susskind in the 1990s and given mathematical rigor by Juan Maldacena in 1997, is that all the information required to describe a volume of space is encoded on the two-dimensional surface bounding it. Information content scales with area, not volume. Applied to our universe, which is increasingly well described by de Sitter space as dark energy comes to dominate, this means the horizon itself carries a specific finite entropy proportional to its surface area. The boundary encodes the interior. The edge contains the information about everything inside it. The horizon is not just a limit on what we can see, it may be a limit on what physically exists, in the information theoretic sense, from the perspective of any observer inside it. So what lies beyond it? 4 layers, from most certain to most speculative. The first is simply more of the same, more space structured by identical physics, seeded by the same inflationary perturbations, populated by galaxies and stars evolving under the same laws. The Vardanyan, Trotter, and Silk analysis gives a minimum of 15 million observable universes worth of content beyond our horizon, implying a total galaxy count around 32 sextillion, 32 followed by 21 zeros, every one invisible to us. This requires no new physics and no speculation. It is what the Planck flatness measurement directly implies. The second layer is finite topology, the possibility that space loops back on itself in a multiply-connected geometry. A hypertorus where traveling far enough in any direction returns you to your starting point. Locally flat, everywhere, globally wrapped, with inflation having pushed any topological identification scale beyond our observational reach. What lies beyond our horizon in this scenario is eventually us approached from the opposite direction. After a journey around the loop so vast, the reflection has never had time to arrive. The third layer is the extended inflationary volume beyond the conservative minimum, the full scope of what inflation created. Many well-motivated models predict expansion factors far beyond 10 to the 26th. Regions that shared our pre-inflationary patch equilibrated with us and then were pushed beyond our horizon by inflation have been running their own 13.8 billion years of history in parallel, formed by the same physics, seeded by the same quantum fluctuations, but permanently inaccessible parallel histories, separated by a boundary that physics will never allow us to cross. The fourth layer is the multiverse, the foam of pocket universes from eternal inflation, each potentially with different physical constants, different vacuum states, different versions of the fundamental forces. This is the most speculative layer and the one that sits most honestly at the boundary between physics and philosophy. It follows logically from the same quantum mechanics that makes inflation generate density fluctuations. It is not arbitrary, but it may be permanently untestable in any direct sense. Whether it constitutes a scientific hypothesis or a mathematical extrapolation consistent with observation is a debate that remains unresolved and worth sitting with rather than resolving artificially in either direction. Every one of these layers is a consequence of the same physics, the flatness requiring extreme fine-tuning, the inflation resolving the fine-tuning by stretching space, the causal boundary that the stretching built into space-time, the dark energy reinforcing that boundary indefinitely. 4 chapters of one story told by one set of equations applied to one universe from its first moment to its last. And the story they tell is that this universe is not hiding itself by accident. The concealment is structural, written into the equations of general relativity, quantum field theory, and the dynamics of inflation as surely as the speed of light is written into Maxwell's equations. The questions we have been circling are not unknown because we lack technology. They are unknowable in principle because the answers are structurally beyond the reach of any possible observation. We cannot build a telescope that sees beyond our causal horizon. We cannot send a probe across the distance inflation opened up. These are not questions waiting for better instruments. They are questions the physics of our universe has placed permanently outside the reach of empirical access. And yet we are not entirely without recourse. The physics governing what lies beyond our horizon also governs what happens inside it, and it leaves traces. The flatness implies the extension. The spectral index confirms the inflationary origin of structure. A primordial gravitational wave detection would measure the energy scale of inflation directly. The matched circles in the CMB that would reveal topology, the bubble collision signatures that would hint at eternal inflation. The evolving dark energy measured by Deci. We can infer what we cannot observe, and the inference, while incomplete, is not nothing. It may be the most remarkable achievement of physics as a discipline that local equations applied to local observations have consequences extending far beyond what any experiment can directly confirm, and that those consequences can be tested through the impressions they leave in what we can access. The observable universe is a window. Small, biased because we are embedded inside it and cannot step outside to check the view, bounded because the physics that made it habitable also made it finite in causal reach, and shrinking slowly as dark energy continues its patient work. But it is still a window. And what it looks out on is not emptiness or silence. It is more universe, incomparably more, formed by the same physics, under the same laws, carrying its own 13.8 billion years of history we will never read. The wall is not the end of the story. It is the edge of the chapter we are in. The universe did not simply grow too large to see. It grew in a way that guaranteed we never would. And perhaps the deepest thought to carry quietly out of this into sleep is this. The fact that we know this is not a failure. It is science, doing exactly what science is meant to do, following the mathematics wherever it leads, even past the edge of what any experiment will ever confirm. Even to the uncomfortable understanding that the most important questions about the structure of reality are permanently beyond our observational reach. The equations reveal their own limits. The data tells us not just what we see, but how much we are not seeing. The wall was not built to frustrate us. It was built by the same process that built us. The inflationary epoch that smoothed our region of space, seeded the structure that became galaxies and stars and planets, created the conditions for something like us to exist that same epoch, in the same fraction of a second, drew the horizon we will never see beyond. The observer and the boundary were created together. We are not separate from the thing that hides reality from us. We are a product of it. The observable universe is not a cage. It is a consequence. The question of what lies beyond it is not really a question about elsewhere. It is a question about why here exists at all. And the answer, as best the data and the mathematics can give it, is that here exists because the physics that made here possible also made everywhere else invisible. The universe has been explaining itself to itself through the only instruments it has ever produced, that were capable of asking the question. We are those instruments, and if that is not enough to fill a quiet night with something worth carrying into sleep, then I am genuinely not sure what is.